Hello students, welcome back to my YouTube channel HZSRA Maths and Tech Classroom for Mathematics. Continuing our classroom for chapter 1 real numbers, revisiting irrational numbers. Basically this is about exercise 1.3. We are going to solve exercise 1.3 of chapter 1 real numbers. So starting with this exercise is basically based on mainly two theorems, theorem 1.3 and theorem 1.4. So what does this theorem states? That states that let P be a prime number if P divides a square, then P divides a as well, where a is a positive integer, any number a. If P is a prime number and if this divides a square, then this also divides a, where a is supposed to be a positive integer. That is theorem 1.3. Another theorem is root 2 is irrational. What does this mean? This means basically that any prime number square root of any prime number is supposed to be irrational. That is stated by theorem 1.4. So how do we approach this problem? We'll have to prove the irrationality. There are mainly three questions and three sub questions of question number 3. So there are total 5 questions to be solved in this exercise 1.3, and all are based on proving the irrationality in different cases. So how do we start? How do we approach such problems? So I have designed a flow chart wherein we can see that first we'll have to make the assumption that the given irrational number is a rational. Okay, in order to prove the irrationality of a given number, we'll have to first assume that the given number is rational. Therefore this can be written in the form of a by b. Okay, then we'll have to set up the condition that a and b must be co-prime. That means they should not be having any common factors. That is the second condition. The third condition states that third conditions were algebraic turn. That means prove both a and b share a common factor using theorem 1.3. Again coming back to theorem 1.3, where it says that let P be a prime number if P divides a square, then P also divides a, where a is a positive integer. Therefore in the very third step we have to prove that both a and b share a common factor using theorem 1.3. Then the last step is contradiction. That means in the very first step our assumption was that the number was rational and that can be written in the form of a by b, where a and b are co-prime having no common factors. But in the third step we proved that both a and b share a common factor using theorem 1.3. Therefore this becomes a contradiction. That means the co-prime condition is broken. So the co-prime condition is broken. That means the co-prime condition is broken. Therefore the assumption is false. Hence we'll prove that our assumption of the given number being rational is wrong. Therefore the number given is irrational. That's how we are going to approach each and every problem. So that was the basic flow chart of how to approach the problem. The first problem is given as prove that root 5 is irrational. Root 5 is irrational. Okay, so first of all, root 5, again this is the square root of a prime number. Okay, so let us assume to the contrary, that root 5 is rational, not irrational. We have to prove that root 5 is irrational. So our very first step was assume rational and write where it can be written in the form of a by b. So root 5 is rational, where root 5 can be written in the form of a by b, that a and b are co-primes and being not equal to 0. So squaring both the sides we will get 5 is equal to a square plus by b square. Thus a square is equal to 5b square. Okay, thus a square is divisible by 5 as per theorem 1.3. A square is divisible by 5, therefore a is also divisible by 5. Therefore a is equal to 5k. We'll take a is equal to 5k. Now substituting that in the above equation, 5k the whole square is equal to 5b square. We'll have to substitute in this particular equation. So 5k the whole square is equal to 5b square. That means 25k square is equal to 5b square, where we'll cancel 5 and here we'll get 5 5 is 25. So therefore 5k square is equal to b square. Again, by theorem 1.3 we can say that b square is divisible by 5, therefore b is also divisible by 5. That means both a and b are divisible by 5. That contradicts co-prime factor condition. Hence assumption is wrong and root 5 is irrational. So it's easy. The only thing is that we'll have to understand how this thing works. So before coming to the next question, let's understand the summary of the given problem. The isolation strategy for composite irrationals. When an irrational root is combined with integers, do not square both sides. Instead, set the expression equal to r, that is rational, and simply isolate the root. So moving on to the next question, question number 2, which is given as prove 3 plus 2 root 5 is irrational. Again, in question number 3 of 3, we'll start first attempt question number 3 of 3, prove 6 root 2 is irrational. See, both the question where the integer given as 3 plus root 2 root 5 and 3 plus 2 root 5 and 6 plus root 2, the number have to be proven as irrational. So before starting the question solution, moving on to the solution, first let's understand the basic flowchart of how to approach this kind of problem, because previously the only root 5 was given. So the square root of any prime number was given, maybe it may be root 2 root 5 root 3 root 7, okay, but here it is given the combination of 3 plus 2 root 5 or 6 plus root 2. Therefore, how to approach such problem, let's understand. First we'll have to follow the isolation strategy for composite irrationals. These are called composite irrationals. So when an irrational root is combined with integers, do not square both sides. Do not square both sides. Like in the previous question number 1 where we squared both sides, here when the composite irrationals are given, we do not square both sides. Instead, set the expression equal to r, where r needs to be a rational number. So we'll have to assume that r is a rational number and simply isolate the root. So we'll isolate integer plus irrational root, and this whole expression will be taken as equal to r. We'll rearrange the irrational root and the number r minus integer. If the right side is entirely made of rational numbers, the left side must be rational. This instantly contradicts theorem 1.4. What is the theorem 1.4 states? That root 2 is irrational. That means under root of any prime number is irrational. So here we'll have to first isolate the given root, the irrational root. Okay, so let's start and approach the problem. Let's start the problem. Problem 2, question number 2, where it's given that 3 plus 2 root 5 is irrational. So first we'll have to assume that rational r, that means 3 plus 2 root 5 is equal to r. Okay, then we'll isolate 2 root 5 will be taken in the left hand side, and in the right hand side r minus 3 will be transferred from left hand side to right hand side, which becomes where the equation becomes 2 root 5 is equal to r minus 3, where again isolating the root, square root, the root 5 is equal to r minus 3 upon 2. Okay, that's how we'll isolate this thing, the expression. Now since r 3 2 are rational, so r minus 3 by 2 will also be rational. So root 5 has to be rational, which contradicts question number 1, that is root 5 is irrational, or theorem 1.4 also, where we have learned that root of any prime number, square root of any prime number is irrational. So hence prove that 3 plus root 2 root 5 is irrational. Again, coming to question number 3, third of question 3, where 6 plus root 2 has to be proved as irrational. How we are going to approach the problem? In a very similar manner. First assume rational r, where 6 plus root 2 is equal to r, root 2 is equal to 6 minus r, sorry, I beg your pardon, root 2 is equal to r minus 6. Okay, we got root 2 is equal to r minus 6. R is rational, 6 is rational, so both R and 6 are rational, therefore R minus 6 also has to be rational. Therefore LHS is equal to RHS. Root 2 also should be rational, but which contradicts theorem 1.2. Hence the given expression 6 plus root 2, the given composite irrational number is irrational. Okay. Now moving on to the next question. First of question third, where we have to prove 1 by root 2 is irrational. Again it's simply 1 by root 2, so we will take 1 by root 2 is equal to R. Root 2 will become 1 by R, so R is taken as a rational number, so 1 by R will also be reciprocal of a rational number is also a rational, so root 2 is also rational as per LHS is equal to RHS, which contradicts theorem 1.4. Therefore our assumption is wrong. Assumption is wrong. Our assumption is wrong. Therefore 1 by root 2 is irrational, hence proved. Okay, moving on to the next question. Third of question 3, prove 7 root 5 is irrational. Again we'll consider, assume rational R. 7 root 5 is equal to R. We'll isolate a root, that means root 5 is equal to R by 7, where R is R and 7 both are rational number, therefore R by 7 also has to be rational. So root 5 LHS is equal to RHS should be rational, which contradicts question 1 and theorem 1.4 that square root of any prime number is irrational. Therefore it is proved that our assumption is wrong and 7 root 5 is irrational. So these are basically theoretical questions, so we don't have to do too much of mathematical expressions. Just we need to understand the basic concept of theorem 1.3 and theorem 1.4. Again we will be revising for theorem 1.3 and theorem 1.4, where theorem 1.3 says that let P be a prime number. If P divides A square, then P also divides A, where A is a positive integer. First theorem. The second, another one, theorem 1.4, where it says that square root of 2 is irrational. That means square root of any prime number is irrational. Okay, so these two theorems, this exercise was based on particularly these two theorems. So only we'll have to understand, as per question number 1, when directly square root of any prime number is given, we'll have to prove the irrationality of that square root of any given prime number. We'll have to simply assume to the contrary that root 5 is rational. Root 5 then can be expressed in terms of A by B, where A and B are co-prime and B is not equal to 0. This condition is very important, that A and B are co-prime and B should not be equal to 0. Okay, then moving ahead, squaring both sides, 5 is equal to A square by B square, A square is equal to 5B square, thus A square is divisible by B, therefore A is also divisible by B as per theorem 1.3. Now substituting A is equal to 5k, okay, where we will substitute here A square is equal to 5B square, therefore we will substitute A is equal to 5k. So 5k the whole square is equal to 5B square, 25k square is equal to 5B square. Now the expression remains as 5k square is equal to B square. Here B square is divisible by 5, again as per theorem 1.3, B will also be divisible by 5. So both A and B are divisible by 5, which contradicts our co-prime factor condition that A and B are co-prime. But here, as per our expression and result, A and B both happens to be divisible by 5. Therefore our assumption turns out to be wrong. Hence root 5 cannot be rational, root 5 is irrational. That is one way of attempting the problem. Which problem? Where directly the square root of any prime number is given and we have to prove its irrationality. But where the composite irrationals are given, first we have to take the expression equal to R, a rational number, and we have to simply isolate the root which was the case in question number 2, where 3 plus 2 root 5 is irrational, has to be proven. Question number 3 of 3 prove that 6 plus root 2 is irrational. Question number 3 of 1 of 3, where 1 by root 2 is irrational, has to be proven, and 7 root 5 is irrational, that has to be proven. In all these cases we'll have to make the assumption and take the expression equal to rational number R. Okay, now let's summarize this particular exercise. Proof playbook synthesis matrix, that's what we call it. We may call it initial assumption when pure irrational roots are given, okay, and when composite irrationals are given. When pure irrational roots are given like root 5, we'll have to simply consider them as a by b equal to a by b. Simply we have to assume that root 5 is rational, hence can be expressed in the form of a by b, and the co-prime fraction condition has to be met. That means a and b are co-prime and b should not be equal to 0. B should not be equal to 0. The key algebraic step should be square both the sides. A square is equal to 5b square, and then source of contradiction, divisibility rule, theorem 1.3 breaks the co-prime assumption. Whereas in composite irrationals, in the case of composite irrationals, example 3 plus 2 root 5, set the expression equal to r, the rational number. Algebraically isolate the root. That means root 5 should be equal to r minus 3 by 2 after solving the expression, and this result can be achieved. Then after a rational expression equals a known irrational root, root 5 is irrational as per these conditions, but the right hand side r minus 3 by 2 all are rational numbers. Therefore the expression r minus 3 by 2 also has to be rational, which contradicts our the theorem 1.3 and theorem 1.4. Therefore our assumption was wrong, and hence the composite irrational given expression is irrational. That's how we can approach such problems. I hope this must be clear for you all, and we'll come up with the next exercise 1.4 based on 2 or 3 theorems. We'll definitely first discuss the theorem in a very brief manner, and then we'll approach the problem, and how the problem has to be approached, dealt with, that we will definitely learn the concept side by side. Then only the problem solving will be easy for all of us, and it will be easy to understand. Thank you very much. We'll meet in next class solving exercise 1.4. That will be the last exercise of this chapter, real numbers. Thank you very much.